In session 5, we will look over some of the points that we made in session 4 about the use of inferential statistics in general and t-tests and analysis of variance, and we'll move on to some further statistical tests. As we mentioned last time, when we talk about inferential statistics, we invariably carry out tests that calculate some sort of statistic, a number. It could be t or f or chi, various things of that sort. We don't need to do that. The software that we use will calculate all that for us. And in fact, it comes out with a p-value, a probability value. We use that along with the significance level that we've chosen to decide whether to accept or reject a null hypothesis. So as mentioned then, statistical tests produce p-values or probability values. We decide if these are significant by making use of an appropriate significance level. So typically then we use 0.05 as our significance level because we are interested in the 5% at the edges of a typical distribution, which would show us that the mean that we're looking at is significantly different than the bulk of the population, which is in the 95% central region. So if we find a p-value that is smaller than 0.05, this implies that the sample statistic is significant at that level. And in that being the case, we would reject our null hypothesis, the hypothesis in which there's no difference, and accept the alternate hypothesis, H1, implying that there is a significant difference. We use a t-test if we want to deduce whether the means of two different groups are significantly different, or it could be a sample and a population. There are different sorts of t-tests, and we'll discuss those in more detail in the session. We use analysis of variance if we have more than two groups, so it could be 3 or more. And again, there are different types of analysis of variance also. One-way ANOVA examines just one variable, so it could be marks or height or weight. A two-way ANOVA looks at two variables. It could be height and weight. It could be term marks and exam results. It could be length and time. The chi-square test basically compares observed and expected numbers. It's a very useful test because it can use nominal or categorical data. So for example, you can look at different eye colours, you can look at male and female, so you've got the numbers of these categories, but the categories themselves don't constitute numerical data. This is also true of non-parametric data, so data that doesn't conform to a normal distribution. So it's a very useful test for all sorts of things. Correlation is a statistical test that looks at relationships between variables rather than differences, and we use it where we have continuous interval ratio variables, in other words, numerical variables. So for example, in this particular example, we are looking at the test score of students who have studied for different study times or different amounts of time. And clearly what we've got here is a graphical representation using a typical scatter plot. We can draw in a line of best fit which actually shows the relationship, and it's the nature of that line that gives us the correlation coefficient that describes how closely the two variables are linked. Regression is very similar to correlation. We're looking at the line again and actually effectively providing the equation of the line that describes the relationship between two continuous numerical variables. And in fact, regression analysis often will produce the correlation coefficient at the same time. One of the reasons regression analysis is carried out is to enable the value of one variable to be predicted from the value of another. We mentioned earlier that some distributions are not distributed normally. They don't provide that rather neat bell-shaped curve. The shape of the curve could be completely different. Strictly speaking, in that situation, what we have is non-parametric data, and we should not use typical statistical tests to analyse it. There are equivalents. So, for example, T-tests, which we would normally use, can be replaced with a test called a Mann-Whitney test or a Wilcoxon test. If it's a typical analysis of variance that we would have preferred to carry out, we can do a test called the Kruskal-Wallis test. And then if it was correlation we were interested in, we can replace our normal correlation, which we call a Pearson correlation, with one called a Spearman correlation. Not something that we need to worry about too much, just to be aware that there are non-parametric equivalents.